In a previous video, I have shown how you can manipulate the electron and hole density. Let's get a feeling for the typical concentrations for majority and minority carriers in doped silicon network in the dark. Typical densities for majority charge carriers in silicon is 10 to the 16 per cubic centimeter, whereas the density of minority charge carriers in that case would be 10 to the 4th per cubic centimeters. This shows that the density of the majority charge carriers can be many order of magnitudes higher than that of the minority charge carrier. Note that the silicon density in a crystalline silicon is around 5 times 10 to the 22 per cubic centimeter. This means that the total number of charge carriers is much lower than the typical density of silicon atoms. The ratio majority charge carriers to silicon atoms in this example is 1 to 5 million. The density of charge carrier concentration can be described by the law of mass action. This mathematical law of mass action is used in other fields as well, like in chemistry. The law of mass action is used to explain the behavior of solutions in dynamic equilibrium in chemistry. What does this law mean for charge carriers in semiconductor materials? This law tells us that at a given temperature, the product of the electron density and the hole density is constant, independent of the doping concentration. So let's consider intrinsic silicon. This is silicon without any impurities. At room temperature, the electron and hole density are equal. N here represents the electron density, P represents the hole densities. For silicon, the electron and hole density is in order of 1.1 times 10 to the 10 per cubic centimeters at room temperature. This means the product N times P is equal to 1.21 times 10 to the 20 per squared cubic centimeters. Now we consider an N-doped silicon material. We incorporate the density of phosphorus atoms in the lattice, which we call Nd. We assume that all donors give a free electron to the lattice. So it means the electron density N0 is equal to Nd. Now we can calculate the hole density P0. The law of mass action tells us at a given temperature, the product of the electron density and the hole density is constant, independent of doping. So P0 is equal to the square of the intrinsic charge carrier density divided by the electron N0 or N0. The same is valid for p-doped silicon materials. We incorporate boron atoms with a density of Na in the silicon network. We assume that all acceptors take one electron and therefore create a hole density P0 equal to the acceptor density Na. This means that the electron density is N0 is equal to the square of the intrinsic charge carrier density divided by the hole density P0. Let's take an example. We incorporate 10 to the 16 cubics per cubic centimeters phosphorus atoms in the lattice, or in other words, we have a donor density Nd of 10 to the 16 per cubic centimeters. As we assume that all donors give a free electron to the lattice, the electron density N0 is equal to the donor density Nd. Now we calculate the hole density P0. So P0 is equal to the square of the intrinsic charge carrier density divided by the electron density N0. So the hole density is given by 1.21 times 10 to the 20. And if we divide this number by 10 to the 16th, we get the hole density of 1.12 times 10 to the 4 per cubic centimeters. Another approach to excite charge carrier is by light absorption. Let's consider the electronic band diagram again. Let's consider a light photon with an energy equal to the band gap. This photon can be absorbed in a semiconductor material and can be used to excite an electron from the valence band to the conduction band. So light can make a semiconductor material more conductive. However, if we have a photon with an energy smaller than the band gap, this photon is lacking the energy to excite an electron from the valence to the conduction band. This photon cannot be absorbed by the semiconductor material. Another situation is when the photon has an energy much larger than the band gap. This photon can excite an electron at an energy level deeper in the valence band into the conduction band, or an electron to higher energy levels in the conduction band. In these situations, the hot electrons or hole very fast relax back to the lower energy positions. For the electron, this is the bottom of the conduction band, and for the hole, means this is the top of the valence band. This extra energy is released as heat and will result in heating up the semiconductor material. So the rest energy, which is the photon energy minus the band gap energy, ends up as heat. Finally, in this block, I would like to discuss how light absorption affects the charge carrier density in doped materials. So let's consider again the situation of majority to minority charge carriers of 10 to the 16 per cubic centimeters and 10 to the 4th per cubic centimeters. Now let's assume we generate 10 to the 11th per cubic centimeters of electrons and holes by light absorption. What will happen to the density of the majority and minority charge carriers? So we simply add up the numbers. What you see is that the majority charge carrier density is not affected by the light absorption. On the other hand, the density of the minority charge carrier is drastically affected. Its density is increased with 7 orders of magnitude. This is an important conclusion which we'll need to understand the working principle of solar cells. In doped semiconductor materials, light absorption has only effect on the density of minority charge carriers. In the last 3 videos, we have discussed how to excite charge carriers in a semiconductor material by temperature, doping, and light absorption. The next question is, how do those charge carriers move around and what makes them move around in a semiconductor material? I will talk about that in the video lecture where we are going to discuss the transport of charge carriers. See you back in the next video lecture.